Justin. Thank you for the introduction and also for the opportunity to present to the EarthScope community. So I will say off the bat that even though this is an EarthScope webinar, that I'm really going to be talking a lot about mostly offshore electromagnetic imaging results, but I will at least dabble in some ongoing projects that we don't necessarily have results from yet, but that are utilizing the magnetotelluric instrument facility that started off with Pascal and is now with EarthScope, that really enable me and others like me, same interest, same expertise, to do the science that we do. And as a matter of fact, this image here is showing the Scripps electromagnetic source instrument that we deep tow for some of the controlled source results I'll be showing. And so it's not something we own here at Georgia Tech, but we really rely on. And so having access to these instruments and these facilities is really crucial for doing the science and making the discoveries that we're able to make. So for today's talk, I will be focusing in really on results related to forearc margins specifically, and in relation to the shallowest structure at the trench toe and going down into the seismogenic zone. And the theme will be really focused on what the role of fluids are. So we know fluids are a critical variable in a lot of these tectonic processes, tectonic and magmatic processes. As you can see from this diagram, the fluids also matter because they're released from the downgoing slab and drive flux melting that feed the volcanic arcs. But for today's talk, really, I'm just going to be focusing in the upper part of this system where it's relevant for earthquake behavior. So if we do have fluids trapped at the plate interface, that leads to some really clear hypotheses that trapped fluids will generate high pore pressures, and those high pore pressures at the fault interface will reduce the effective normal stress on the fault. So presumably they could either lower the plate coupling or make it more likely to have an earthquake rupture sooner rather than later, or maybe limit the size of earthquakes. There's a lot of different ways that fluids might influence the system, and it's gotten a lot of attention, I would say, in the last decades, trying to get at what the role of fluids are for these various processes has been highlighted in a number of studies, and not just EM studies, also several other imaging studies such as seismics, active source seismics included. So that's kind of going to be the theme. I also wanted to show this figure because it gives you a sense of how traditionally we like to hypothesize what might be going on. So this is modified from a figure Damien Safer published some years ago. And the first order idea really is that where we have fluids trapped at the plate interface, maybe is where we have aseismic creep or basically lower plate coupling, whereas where we have dry or where fluids are able to escape either through the upper plate or the fact that they weren't there when the subduction occurred to begin with, maybe those are regions that are going to be less overpressured and therefore more coupled. And so in the context of EM imaging, we see those in terms of resistors and conductors because the fluid, I'll show you in a few slides, the fluids are conductive in nature. So where we can map fluids based on the conductivity or its inverse, the resistivity structure. So EM methods, as I was kind of already alluding to, they're imaging resistivity. Okay, and so this is just a diagram to give you a sense of some of the first order controls. These are by no means the only controls on how resistivity varies with material properties, but some of the highlights here, especially with a relationship to the talk I'm presenting today, are captured in the upper handful of columns. So we have water. So water itself, the conductivity, or again, its inverse, the resistivity, depends both on temperature and the salinity of the water. And so you can see here that the scale bar is orders of magnitude. We can go over 5 orders of magnitude just in terms of the water resistivity based on how fresh it is or how warm it is. In our case, since all the imaging I'll be showing is offshore, we like to treat the fluid as if it were exactly the salinity of seawater. And so what we need to still take into account is the temperature, the thermal structure, if we want to take this property and mix it in with what is otherwise resistive oceanic crust or mantle, and sediments themselves are actually also resistive. It's a mixture between essentially something that's you can think of as an infinite resistor and a conductive fluid embedded in that. And so the resistivity itself will depend on that porosity. And so we can get at that, we can estimate that porosity using mixing relationships such as Archie's law. Archie's is an empirical relationship. There are other types of mixing relationships. So there is a little bit of uncertainty associated with this, but at least it gives us some bound on what the porosity structure is. And so, for example, we take, like I mentioned, the sediments themselves are otherwise resistive, but they're usually highly porous. And so in this equation here, what we're imaging is rho, which is our bulk resistivity. And the equation itself depends on a function of the fluid resistivity multiplied by the porosity to some cementation exponent. I'm not going to spend any time talking about cementation exponent. It is an important variable that we usually, in a sense, kind of guess. We have decent constraints on what types of values it might have, but it is another source of uncertainty in these types of, when we apply these types of equations. What I wanted you to take away today is, although I'm going to be focused on porosity of the shallow part of the margin, which is probably dominated by seawater, or something maybe slightly less saline than seawater if there's dehydration and therefore freshening of those pore fluids, it's not a bad estimate to assume it's seawater. And then again, we're applying that thermal structure. But let's say we were more interested in actually the composition of the fluid. Our sensitivity allows us to get at that. And while I'm not going to talk about it, it's worth a take-home message I would like you to get away from, take away from this talk, is that we can constrain composition of fluids and temperature of fluids if we can say something about what the porosity is independently. So it gives us a lot of interesting problems that we can tackle by being able to constrain what the resistivity structure is with our geophysical imaging. Okay, so I wanted to give, since most people here are probably from seismics, geodesy, and not necessarily experts in EM, I wanted to just give a really quick explanation of how the method works. We start off with Maxwell's equations. So we have Faraday's law of induction, we have Ampere's law. And what we essentially do is we decouple those equations to get at our governing equations, where we have just, it's not shown here, but we have just electric field with respect to electric field and magnetic field with respect to magnetic field. Okay, so this is somewhat shown here, actually. And what I want you to see in here is that first we have our induction part of this. Basically, when we have a time-varying magnetic field, that induces currents in a conductive material. And the amount of current that's induced depends on the electrical conductivity of that material. So that sets us up for doing passive imaging, which I'll show in a figure in a sec. In addition to that, we can ourselves generate a man-made source of electric current, which is signified by this JS. So this could be our transmitter, for example. So we can do both passive imaging that relies on time-varying magnetic fields for the current source, or we can generate currents ourselves with some type of transmitter. And ultimately, we're constraining this sigma variable here to get at the electrical conductivity. So these methods are induction EM methods, and they're governed by the diffusion equation. And so that gives you a sense of what kind of resolution we might have from these types of observations. They're not going to be the resolution of wave-based methods like seismics, but they're also going to have a much more resolution technically. Potential fields don't have any resolution. We impose those based on how we know this Earth's interior structure to vary spatially. So it's on the order you can think of your mind of the size of the feature versus its depth is kind of the type of resolution. That's not completely true, because the higher the contrast in the resistivity is, the better we can resolve narrow features. But usually in our inversion products, they'll be smeared. And so we have to do additional tests to say how narrow or how broad is a particular anomaly really. And you'll get a sense of that by looking at the images in this talk today. Okay, so this is how it works for the magnetotelluric. So magnetotelluric is just another way to say the passive electromagnetic induction-based method. So magnetotelluric relies on naturally time-varying magnetic fields, and that really comes as a product of the fact that there's solar wind bombarding Earth's magnetic field, so the geomagnetic field, and that wind you can think of as literally a wind. Its speed varies with time, and so therefore generates a time-varying magnetic field. And those time-varying fields induce currents inside the relatively conductive solid Earth. The atmosphere is highly resistive below the ionosphere, whereas the solid Earth itself is several orders of magnitude more conductive, relatively speaking. In addition to that, we can generate our own field here. So this is the transmitter part of this, where we deep tow. In this case, this is showing you how it works in marine environments. We deep tow a dipole-dipole transmitter, inject current into the seawater, and that eventually propagates through the solid Earth, and it's recorded by receivers along the way. And so the amplitude of those fields and the phase tells us about how the resistivity structure varies spatially and with depth. So these are frequency. We work in the frequency domain, and you can think of frequency as basically being your depth. The lower frequencies you go to, the greater depth sensitivity your data have. Okay. All right, so I wanted to give you guys a sense of what the instruments look like, what is the procedure of collecting and analyzing this data. So we record electric and magnetic fields in two orthogonal horizontal directions in the case of seafloor data. So this is, you're looking here at a Scripps ocean bottom electromagnetic receiver, which houses the data logger and the batteries. And the sensors attached to that are these induction coil magnetometers. You can see these tubes, blue tubes, they're going in two orthogonal orientations for measuring the magnetic fields in X and Y. And then on the ends of these long plastic arms are electrodes that measure the electric field. And so these are on 10-meter arms, and that's because the larger separation distance you have, the larger signal you have, and then you can get electric field simply by taking what your voltage reading is and dividing it by the separation distance of your electrodes, since the electric field has units of volts per meter. And so the longer we can make this, the better our signal to noise ratio effectively is. And on a ship, 10 meters is about as long as we can get away with. There are also long arm instruments that we can deploy, but those take significantly more effort but might give you much higher noise, much higher quality data if you're really trying to get at, let's say, controlled source for imaging the deeper mantle. Okay, so here I'm just going to show, Carrie Key made this really cool video. Carrie has a lot of cool media that I always lean on for my presentations. This is a video to give you a sense of what the natural fields are doing all the time around us that we don't obviously feel. This is from the MOCA project. Basically, we deployed about 50, in total, I think 70 seafloor receivers, but these 51 receivers shown here were recording simultaneously offshore Oregon and I think southern Washington for some of this northernmost line. And what you're looking at when I played the video, the blue vectors are the magnetic field, the red vectors are the electric field. And before I even play it, you can see that predominantly they are orthogonal to one another, which is what we would expect based on Maxwell's equations, right? The other first order behavior you see is that the vectors are larger in the shelf, and as you get to deeper and deeper water, they become smaller and smaller. That's showing you the fact that the source fields are attenuating as they travel through the highly conductive seawater. So their amplitudes are decreasing. That seawater is also a great news for us because it filters out essentially cultural noise, which is a big problem for MT when we do it onshore. Okay, so the more interesting part of this is to show you the video, and you can see this is on the scale of several hundred kilometers, and all these vectors are dancing together. And every once in a while, you'll see a big pulse of energy come from ionospheric activity and get recorded by these receivers. And that's when these vectors really light up, become larger, and start dancing around more. So there's a lot of neat stuff happening in the electromagnetic world, and it's pretty, to me, really neat to see this video just because it shows you what our source fields are doing all the time. So when there are large, let's say a solar flare going off, there's going to be a big burst of energy. You're going to see this these vectors get quite large and start dancing around a lot more. So if it's always really, really quiet, it can mean you need to deploy for slightly longer. But in practice, we found that generally speaking, the latest instrumentation technologies allow us really to collect good data regardless of how strong our natural source activity is, as long as we're in a relatively quiet environment, so we don't have noise sources to deal with. Okay, so we take that time series data, as that was fun to look at and all, but that's not really, the time series itself is not really what we're interested in. We take it and Fourier transform it into the frequency domain. So our modeling is applied to this data that's basically a complex value, a complex number that we break up into amplitude and phase, and it varies as a function of frequency. So in the MT world, that offshore usually means between about 1 second to tens of thousands of seconds is our band of interest. Onshore, we can go to much higher frequencies because, again, you don't have that conductive seawater filtering out the high frequency sources. And so we can get at much shallower structure when we deploy onshore instruments. For that same reason, the fact that the seawater attenuates the high frequencies, that's why we have our controlled source deep towed instruments, is to compensate for that lack of energy band and use a high frequency transmitter source, and then get us that sensitivity to the shallow structure that we're interested in. Okay, so we take our data and we apply geophysical inversion, and there's a lot of different types of inversion. This is an area of expertise all unto itself. In this figure here, I'm just showing you a 2D deterministic inversion using Occam's method. We take our data and we invert it, and so the color blobs you're seeing here from red to blue is that conductivity structure, where you're in blue, just like I showed you in the previous diagram a few slides ago, is the resistive end of the color scale, and the reds are the conductive part of this color scale, okay? And in the end, what we really want to know is, what does this all mean in terms of physical properties we care about to understand the geology and the tectonics or magmatic processes? So that's kind of, in a nutshell, what an EM practitioner does. We have to dabble in all aspects of this to ultimately get a result that we can interpret for geology, which is mostly what we're interested in. So really quickly, I will show you offshore what that looks like. You saw the instrument already. We've gotten pretty good about deploying these relatively rapidly. If ship time aside, to get to your next deployment station, it takes us about a half hour to assemble and deploy each receiver. And if that's all we were doing is just deploying receivers, we would be getting just MT data. So these receivers are broadband loggers, which means we can simultaneously record MT and CSEM. And so if we're deep towing a transmitter, we can tow at about 1.5 knots on average. And so we can get a 200-kilometer profile in about 10 to 12 days ship time. Caveat being, if I want to get MT data to longer periods to really get at structure in 100+ kilometer depths, I may want to leave the receivers down a few extra days to make sure I have enough time series to get good estimates at those longer periods. So we deploy the receivers. The recovery takes a little bit longer just because it takes a little longer to go through the water column. And then the fun part of the deep towing really is deploying this, the antenna behind the ship. It's really heavy, it takes a lot of people. Beyond that, once this transmitter is in the water, we have to make sure people are awake at a screen so that they don't fly this thing into the seafloor. It's slow going, but we try to keep it at about 100 meters off the seafloor for safety reasons. If it's really flat seafloor, we might push it down a little bit more. But usually in subduction zones, it's very rarely flat seafloor, okay? And then we recover and repeat. And so we can do this in profiles in terms of both joint MT CSEM, or if we're just trying to get an MT array, we can deploy an array of receivers and let them record the natural sources. On land I'm learning in the last couple of years, I've had the pleasure to do a few onshore projects, is all a significantly more energy intensive affair. We have to dig holes, and this can take anywhere from 1 to 2 hours, depending on what the properties of the ground are where we're digging. And we're essentially, again, installing electrodes and magnetometers. What's different here is that because we're on land and we just need a cable to connect electrodes, we try to increase that electrode offset from, instead of just 10 meters, we usually like to have at least 50 meters up to 100 meters to improve that signal to noise ratio. And then we have our induction coil magnetometers. What's different on land as well is we can record, if we're interested, we can install vertical oriented coils, and that's to get at what are called tipper data, and it helps you see where conductors are aligned, but I won't be talking about that today. So on average, a team of 4 people, if you have your permitting and depending really on site spacing and land access, typically we can recover and deploy 2 sites a day on average. And the nice thing I should also say about MT, these sites don't all have to be deployed at the same time. You can record a couple sites at a time and leapfrog them. You don't have to have all of the receivers out simultaneously to do the MT analysis. Okay, so let's get into the actual science now. I probably talked too long about intro, so we'll see how much time I get to really spend on this. I apologize for that. So what I'm going to be showing you today is basically a growing number of results as we collect more and more of these offshore EM data sets at different subduction zone margins. And so I'll be showing you results from offshore Central America, a profile, the very first profile of its kind, really, with this density of stations and both MT and CSEM data, which was collected in 2010. And then we've expanded since then to collect data sets at the Hikurangi margin, offshore North Island, New Zealand, and the Alaska margin, Alaska Aleutians margin as well. And the take-home message really at the end of this talk, if we get there or not, is that fluids, the structure is highly variable depending on where you are regionally. And the fluid distribution depends on where you are regionally. And so like we already kind of knew from seismic imaging results, if you want to know about the influence of fluids on the tectonic processes, you really need to know what the structure looks like at that margin. It's not necessarily a simple, coherent story that applies everywhere globally. Okay, so let's dive in. I'll be pretty brief about this one because this result has been out for a while, but it does highlight one end member of what the structure can look like at a subduction margin. So this was the Serpent project. And so we deployed a profile of receivers about almost 300 kilometers long. 2/3 of that was also collected CSEM data with a deep tow transmitter shown by these white receivers and the blue lines. And the motivation for this project really was to just try to understand what is the distribution of fluids, both in the incoming plate and in the forearc margin. And primarily, as you can tell from the acronym for this project, can we image fluids going into the incoming plate through bending faulting, which was already imaged really and hypothesized based on seismic results. The very first of these results was actually this profile here from Renero et al. 2003. So you can see we're pretty close to where that paper's profile was collected. In our case, we're also co-located with active source seismics. And so that allows us, and this is ongoing work really, for integration of both the seismics and EM imaging to really more definitively get at where the fluids are and what their properties are and how they're affecting processes. So this is the inversion result. I won't spend too much time on the incoming, actually I won't spend any time on the incoming plate, but it's a nice story because you can see what's red is conductive. We have a thin layer of conductive porous sediments, and that very quickly becomes blue because the porosity is essentially decreasing exponentially as you get into the crust and upper mantle. But where there are bending faults, we do see these subvertical tongues of higher conductivity indicating fluids really are entering the system, as had already been expected from seismic imaging studies. For this talk, I'll be really just focusing in on the forearc and what we learned from that. So first, this is a non-accreting margin, and we can see these incoming sediments are basically completely subducted with the slab and form the plate interface. And some of these fluids are escaping through the upper plate and feeding fluid seeps that have been mapped at the seafloor, including in this region as shown by these blue cylinders. So we can do a little more than just that image, right? So the upper plate you can tell is relatively low porosity because it's more resistive. The plate interface is relatively high porosity because that's where the porous subducting sediments are. We can also estimate that porosity. And so to do that, what we first have to do, remember these are diffusion based techniques, right? So there's surely some smearing of this conductive anomaly when we're imaging it. The good news is, even though there's smearing, it might be smeared, but the total conductance is really well constrained. So what that means is that even though we don't know necessarily how thick it is, we take that conductivity thickness product, we can get a decent estimate of the total water budget in that layer. And so that's what we're going to do here. We're going to define a channel thickness. So based on what we know the incoming thickness of the sediments are, they're about 400 to 500 meters. And what we know from compaction studies, you can see that in the black and gray line, we expect the sediments to thin relatively rapidly from the compaction. Whereas our estimates of the thickness are tens of % larger than that. And that's showing you that smearing effect. But by constraining what that thickness is based on the gradient and the resistivity, we can now also estimate the porosity and any depth through that layer and integrate that to get the total water. And this is where we see that we're actually in really good agreement with what we would predict based on the compaction studies for how much water is at the plate interface. These two different colored bars are just to account for the uncertainties in temperature and the cementation exponent. And so they happen to align perfectly with these two lines, but that's just a coincidence. But what we see on top of those predictions from compaction studies, we're clearly seeing variations down dip, where there's some parts of the plate interface that have more water than other parts. And then we get to this interesting anomaly, which has so much water in it that it would basically be more water than we know is entering the subduction margin at the trench axis. And so that leads us to say, sorry, I forgot to click for these bullet points here for you. This large water budget anomaly here, it's very likely that this is part of the upper plate rather than a feature that's part of the subducting plate. And then there's not really a clear channel down dip, and that has to do with our loss of resolution because this is controlled source data, and so our depth sensitivities may be down to 10 kilometers at best, but we're also losing our resolution on top of the sensitivity, okay? So what does this mean in terms of the theme of the talk is seismogenic zone. What does this mean with respect to the seismogenic zone? So what's interesting about this region is that this was actually where modern seismic instrumentation recorded the very first tsunami-genic earthquake, which occurred in 1992 offshore Nicaragua. So it's actually technically a tsunami earthquake, and a tsunami earthquake has a very specific meaning. It means an earthquake that's relatively low magnitude, didn't cause as much shaking relative to the size of the tsunami it generated. And you can see here, even within a year of, or maybe a little more than a year after this earthquake occurred, Kanamori and Kikuchi wrote this Nature paper suggesting that this slow tsunami earthquake likely has to do with the fact that this is a non-accreting margin where it's sediment and therefore fluid rich along the plate interface. And that jives perfectly with what we imaged as well. But we can say a little bit more than that. What's also interesting about this earthquake is that where the earthquake radiated seismic energy and the seismic slip inversions are actually different from the tsunami slip inversion. So these yellow colors here are showing you where seismic slip inversions are saying the slip occurred during this earthquake event. But in reality, the tsunami source inversions require slip to extend really all the way to the trench axis to generate the size tsunami that was observed at the coastlines. And so that's what's shown here, the yellow patches from the seismic source inversions, and this red box is showing you predicted part of the fault that slipped due to the tsunami source. And so our thinking is that maybe this has to do really with the structure that we're imaging. I'll go back a slide here if I can. I probably cannot, and that's okay. Let's see, actually I can. Okay, so the onset of that upper plate anomaly happens right about here, right where you see this fault extending across the margin, where the slope of the seafloor suddenly steepens in the middle of the forearc slope. And up dip of there is where we see the simple high conductivity channel where a lot of fluids are along the plate interface. So our thinking is maybe this is telling us why seismic energy wasn't radiated up dip, is it has to do with the fact that there's some change in the material properties at the plate interface associated with those fluids. Okay, so very quickly, this is where I get to advertise and say nothing more about this project because of time and really because the results are quite preliminary. This is in the same region now. We're in Nicoya Peninsula, just south of that profile, and it's very similar question. This is an area where there's slow slip events and hazardous earthquake ruptures, patches in different parts of this margin. And so we thanks to the EarthScope MT facility, we went out and deployed 42 of these receivers, and we're trying to get at now, what are the lateral variabilities? I just showed you an image of just in a profile down dip, but how does the distribution of fluids vary laterally, and how is that associated with the earthquake slip behavior and plate coupling over time? So this is work being led by my student Oliver Azevedo, and really kicked off, and a key person in this is Darcy Cordell, a former postdoc who's now at the University of Alberta. Okay, so moving on. That was sorry for the aside there. So the next project we did was at Hikurangi. So this is offshore the North Island of New Zealand. And this project, honestly, we still have a lot more work to do. We collected the data in late 2018. And you can see here that the one advantage of working here is that not only did we collect a really large scale project offshore, but there's also a beautiful onshore data set that has been collected over the years by our GNS colleagues. And so this is really going to amount to the largest amphibious MT survey to date. I should say that we're just starting to kick off doing that integration of both the offshore and onshore data sets. But today I'm only going to focus on results from the northern profile here and the southern profile here, and stay tuned for future publications to do with this awesome data set. So the motivation for this now, I intended to skip the slide, so I'm going to skip it for the sake of time because it's shown here too. So these are figures from Christine Chesley, who led this effort for her PhD. What you're seeing in the red here are contours of slip patches, a cumulative slip from slow slip events across this margin. And so what you see is we have shallow slow slip occurring in the northern half of North Island, and deeper slow slip, but expected therefore to have higher plate coupling in the southern half. And so our question ultimately is, what's the role of fluid? Are fluids somehow responsible in where you have slow slip events versus where you have high plate coupling and the expectation that there will be a larger megathrust earthquake event in sometime in the future? So here for now, at first I'm going to show you what the results look like from the northern profile, where we do have shallow slow slip, and that's shown here. So again, this is work that was led by Christine Chesley. And right off the bat, what you can tell is when you compare this to the Serpent or Nicaragua results, it's substantially more heterogeneous. So we have a lot more heterogeneity in the conductivity structure, both in the incoming plate as well as in the forearc part of the system. So here it is now in 2D view to give you a better sense of just how substantial that heterogeneity is. There's a really cool story here having to do with the Taranganui Knoll. I apologize for mispronouncing that name, including where we know there's a normal fault. We see this tongue again. This is a large igneous province. There's a really chaotic, heterogeneous structure of the seamount itself. But today I'm just going to talk about the forearc side of this. So we know there's an incoming plate seamount, but what we also know is that there's a comparable size seamount subducting here. And then if I go back one slide or two, that's the outline shown here. This is where that subducted seamount is, and you can see here in the bathymetry, this is where the incoming plate seamount is. So just take this and rotate it, and they're comparable in terms of their spatial skills. When we overlay what we know about the seismicity and the tectonics, this is a very busy slide, but it shows you some really exciting, or really interesting at least, correlations between seismic behavior, where the faulting is based on controlled source, or excuse me, active source seismic imaging, so MCS data, multi-channel seismic imaging, and where that correlates with our conductivity structure. So right away, again, here's where the projected plate interface is. You can see it's highly heterogeneous in its resistivity structure. There isn't just this thin, simple conductive channel of high porosity stuff being subducted. It's way more complex than that. And then you have what we're seeing here is the seamount. It has a really sharp resistive peak that actually mimics the structure that we see for the incoming plate seamount. That it might be broader, but it has a resistive peak that maybe has to do with a strong igneous core or something of the sort. And then there are these upper plate anomalies, and these upper plate anomalies, especially C2F, correlates with a lot of microseismicity associated with a past slow slip event and repeating earthquakes as well, shown by the stars. So these are relocated events, and they match up pretty well with where we're seeing this red blob, indicating to us that the seismicity may be capturing fracturing or damage that's occurring associated with the passage of the seamount beneath the forearc margin. Okay, so again, this is highly heterogeneous structure. There's prominent conductors and then lack of conductors along the plate interface. And this conductive anomaly here, C2F, which is in the upper plate, is correlating with some of that seismicity from these slow slip events. So this leads us to wonder, is it heterogeneity plus a rough subducting plate that might be responsible for why we have slow slip here and not in the south? And I should note that it's not like we're the first to suggest this. Actually, even there's a paper by Barnes et al. Based on IODP drilling that suggested that it was heterogeneity that's responsible really for the seismic behavior in the northern margin and part of the margin, and including the occurrence of repeating slow slip events. So it's nice to see that we're seeing something comparable, but from the perspective of the fluids and the porosity structure. All right, so hopefully when I show you this image, it'll convince you that that very likely is the case, because now I'm going to show you the inversion result from the southern part of this. And what we see is that it's honestly kind of boring by comparison. It's effectively 1D vertically varying structure. We have a much thicker sediment section coming in with the incoming plate and subducting. You can see this tinge of tilting blue that's indicating where the plate interface is. But overall, the first order structure is quite homogeneous. And remember, this is also where the plate is locked and there's no shallow slow slip. So it does seem to put some emphasis on that interpretation that this is likely. Okay, and I already said this, but I just wanted to highlight, if you want to see the latest from the onshore results, they have a really nice 3D model incorporating a large fraction of this onshore data set. I encourage you to read the paper by Wiebke Heiss that came out in GJI late last year. And Christine is working, myself and Christine are working with our GNS colleagues to jointly invert this. And we're really excited to find out what we see, because already the onshore stuff is showing that there's correlations between the strain rates based on geodetic observations and where we're seeing conductors and resistors. So surely there's a lot more interesting stuff to learn. Okay, so it is 40 minutes into this, so I'm gonna kind of zoom through this really fast, and I apologize for that. But for this last bit here, we collected 3 profiles of active source, so basic controlled source EM, and also these all collected MT data, this time now off the Aleutian Alaska margin. And conveniently, this survey occurred in summer 2019, and a year or so later, we had these 2 earthquakes, one of which partially filled in the Shumigan gap, this seismic gap. And so that's what I'm going to focus on for this last little bit of the talk here. All right, so this is just to show you now, these are all our lines, line 2, line 3, and line 5 are co-located with active source seismic project, the Aleut seismic experiment. And 3 and 5 of the Aleut seismic experiments also had OBSs, so they were able to do wide angle tomography to get at the velocity structure, allowing us to ultimately make some really interesting comparisons. This is showing you what the plate coupling looks like. We have the Shumigan gap, where again, there's a lack of historical record of a large megathrust earthquake, whereas the Yosemite segment, which is slightly more locked, has had a historical megathrust earthquakes in that region. So the seismic active source seismic results showed something really interesting. They show that the structure at the plate interface of the Shumigan gap actually indicates that you don't have a lot of fluids trapped at the plate interface. Whereas for the Yosemite segment, where there has been earthquakes and an increase in plate coupling, you do have this fluid-rich subducting layer of sediments. So this kind of flips our hypotheses on their head. And what this led the authors to suggest is that it's a irregular plate boundary rather than fluid. So a rough seafloor subducting rather than fluids that's responsible possibly for the low plate coupling in the Shumigan gap. Again, this is just to show you to show you the slip contour. I think this is the 0.5 meter slip contour, if I remember correctly, from the July 2020 Semyonov earthquake, and where our profile is. So I'm going to show you MT inversion results of the white squares only, because the red ones, they were 2 3-dimensional, and so we couldn't analyze these with 2D methods. And you can see they overlap with where the fault slipped from this event, at least at the western edge of it. So what's interesting is this event seems to have ruptured, initiated somewhere near where the Shumigan-Semity boundary is, and then propagated westward into the Shumigan segment. All right, so this is our inversion result, and we just show you this inversion result right off the bat. It looks like giant blobs, and it's hard to understand what might be going on. And so this is why it's very valuable to be able to draw on these, where the plate interface is, what the architecture is that's derived from active source seismic imaging. And so you can see here, this is approximately where the plate interface is. And then here is where we have the upper plate moho. And then we have also this through-cutting normal fault in the upper plate, and this large sedimentary basin known as the Senac Basin. And from the EM imaging side, we're seeing these 3 primary conductors, C2, C3, and then C1, which is associated with the fluid-rich sediments of the basin. Okay, so when we overlay on this seismic velocity contours from the wide-angle tomography, we see some really nice correlations in agreement. We're to first order capturing the geometry of the sedimentary basin in our MT imaging. We also see that there's these high velocity in what are potentially intrusive features in the upper plate, shown by the 7 km/s velocity contour. The first one of which actually correlates with a resistive feature that pulls up here in our inversion. And where there's a dip in that contour is also where we have this conductive anomaly associated likely with fluids. So again, this seems to agree. Remember, the MT data stops not very far offshore, so this seems to agree with the lack of fluid story argued by the active source seismics, both in the wide angle and in the reflection imaging, that there really is a lack of fluids at the plate interface, at least in the shallow portion of this margin here. Yeah, it's low plate coupling, right? So I'll just for time skip this slide here. And now when we overlay the a record of seismicity in this region. So this is, I believe, up to 30 kilometers off our profile, condensed onto our cross-section here. We see an interesting correlation of where the seismicity is occurring, and also embedded on this is the reflection image. And so there's this previously observed thick band of reflectors that was interpreted as possibly being due to fluids enhancing the reflectivity. And based on our image, that seems to indeed be the case. We have some fluids being sourced from dehydration of the slab mantle, which I won't discuss in this talk, and so I refer you to the paper to learn more about that. And those fluids are migrating upwards into the upper plate and influencing the structure here. In addition to that, this is showing you the slip contours from this event, at least along this profile here. Where the earthquake slipped in 2020 is where we have a relatively conductive structure around the plate interface in our inverse model. And so that's suggesting to us maybe that it's, in addition to possible asperities that are creating some localized locking, that maybe the fluids here are instead enabling dynamic rupture propagation for this particular event. Yet fluids aren't required for plate coupling updip. All right, so I'm really going to zoom through this here for the sake of time. I apologize for talking so long, but this is the CSEM result that my student Yinchi Lee has been working on. I only showed you the MT, so this goes all the way to the trench axis, and it does seem to indeed indicate, overlaid on the reflection seismics, by the way, it does seem to indeed indicate that there's not all that much fluids at the plate interface. Maybe there are in the first 20 kilometers, but very quickly decreasing as you go to greater depths. Besides that, it's just awesome to see this first order agreement of where the sediments are based on the seismic reflection and where things are conductive based on our CSEM imaging. I flipped this, by the way, reflected this, so that's probably messing with your brain right now, the orientation. But we do want to overlay here what the MT result looks like, and you can see the MT has that depth sensitivity that we're lacking with with a controlled source EM. And so the future work really is to jointly invert the controlled source and the MT data to get at the fluid distribution for this whole line. And then also again for line 3 in the SMIDI segment, which I haven't talked about and I'm not going to talk about at all today. Okay, so I'm just gonna go straight to the conclusions here. Sorry for dashing through some of those slides. The takeaway for me really is that the fluids are influencing subduction seismogenic zones in many ways, and they require regional studies. And I don't think that's some kind of mind-blowing statement I'm making. I think many of you probably already felt the same way, but it's great to see that we can really add context and some valuable constraints on how those fluids are distributed and regionally how they're affecting one seismic zone versus another. I won't reiterate what I've shown, but you can read it here. And so the last thing I'll say is that this is really an exciting time for the EM community in terms of what we're able to do with our advanced modeling codes and the access to these state-of-the-art instruments. And so I'm very optimistic and look forward to seeing what future both onshore, offshore, and really especially amphibious studies are going to come out of the fact that we have access to these first-rate instrumentation fleets. And with that, I appreciate your attention and thank you for your time.
Excellent. Thank you so much, Samir. What a fascinating talk. We've had a few questions come in thus far, but for those of you that are tuning in, if you have a question for Samir, please feel free to go ahead and enter that in the Q&A box and send those in. I'll just start off here with our first question that comes in from Jeff Abers. He says, in the Schumagen image, is C3, or the deepest anomaly, is it coincident with the lower zone of the double seismic zone?
Oh, yeah. Great question, Jeff. So maybe I shouldn't say all this here, but the one thing that got me super excited when we first saw this inversion result is that it seemed to match up with where there were some earthquakes from the GCMT catalog, from the global catalog in terms of the beach balls, right? And they all seem to cluster here, but then I later learned that those depths are not necessarily reliable. And so this is something I think we need to look into. I have a feeling that it does seem to, the deeper earthquakes, I think, start about this distance from the trench axis, and they are of a comparable depth. Now, obviously, our blob is very large in spatial extent, but yes, I think there is a hint that these might be related, which opens up really exciting possibilities of explaining those earthquakes with dehydration, or at least the onset with them with this pulse of dehydration based on C3.
All right. I was curious, Samir, just from an instrumentation perspective, have there been any significant changes with the type of MT instrumentation that you've been using to do marine studies in recent years? Has it come a long way, or is it pretty established and like fixed at this point? Or do you see improvements coming down the line?
Yeah, so I think that the major advance occurred around the turn of the century, and so the Scripps lab, really led by Steve Constable, and at the time Kerry Key had his hand in this as well. Through industry support, we're able to build this fleet that of the seafloor receivers that have definitely need some updates, but overall, I would say the technology has at this point become mature. So, for example, they still use CF flashcards, which are no longer produced for recording the data. And so we need to update the loggers and maybe use embedded flash drives, right? And things of that nature. But I think in terms of the overall technology, at this point, it's reached a state where it's mature, and really it's what it's enabling me to do what I love to do and go out and collect these data sets.
Yeah, no, they're good. It's great data. Okay, a couple other questions. One here that asks, what is the typical frequency of the obtained data from the receivers?
So that's a great question, and I kind of jumped right over that detail. The receivers themselves so the loggers can record up to 500 hertz. Usually when we do our joint MT and CSEM surveys, we have them record at about either 62.5 or 125 hertz. Or if we're doing empty only, we can reduce that to, let's say, maybe around 25 hertz is okay. So that's just in terms of the logger itself. In terms of the data of interest, because of that attenuation in the seawater, when we're in, let's say, on average 3 kilometers, so typical ocean basin depth, 3 to 4 kilometers, the shortest period MT data we can get because of that attenuation of the natural source is on the order of 20 seconds. So we deep tow a transmitter, and the transmitter we typically use anywhere between a 1 second to 4 second fundamental frequency, and then it's a boxcar function. It's a fancy boxcar function, and it has harmonics. And so our data that we're inverting for CSEM usually are on the order of between 1/4 hertz up to about 3 1/4 hertz. If you really want to get at shallow structure, we can push that up to 10 hertz. And there are folks who have done that, for example, for gas hydrate imaging, because gas hydrates are resistive and in the very near surface of the seafloor. And so they'll rely on the higher frequencies that I myself am interested in for these studies, because I'm trying to get at the top 10 kilometers of the seafloor.
Yeah, maybe a related question here from Kellen Wang, wondering if you could briefly explain how the resolution changes with depth.
Yes, how the resolution changes with depth. So it's difficult to get a satisfying single answer to this, but it's reasonable to treat it as the resolution decreases gradually with depth. So a reasonable rule of thumb, I would say, is, let's say you're interested in a feature at 100 kilometers depth. Then it's probably going to hard to image that feature if it's any thinner than around 10 kilometers. So maybe 1/10 of the depth you're looking at. However, there's a huge caveat there, because it depends on the conductivity contrast of that feature. So if, let's say, we're in a 1 million ohm meter half space and you have a 1 ohm meter thin layer, your resolution will be substantially higher because you have 6 orders of contrast in terms of the resistivity anomaly. So for that reason, there's no satisfying way to answer it, but I think that gives you a sense. So I would say on the order of like 1/10 of the depth you're looking at is not a bad guess for the resolution. Lateral resolution is a different story. So laterally, especially with the CSEM data, laterally, because we have transmitter points all along, we can have really good lateral resolution of features, which is actually why we're able to image the bending faults with such high resolution. And it has to do with the fact that we have a significant amount of transmitter points. So this data it's not just the receivers, it's also the transmitter locations. And so we can resolve some narrow features in the near surface with higher resolution.
So we've talked about variation in resolution with depth and laterally, and we have a question here now about another dimension. It says, is the data sensitive enough for conducting repeating measurements along the same profile to look at temporal variations in the resistivity structure, or would that change likely lie within the error range?
That's a fantastic question. And it's a fantastic question because I think it's an open question that there are many people who are, for example, now trying to get at that. One of my colleagues has MT sensors deployed on a number of volcanoes, including in Alaska, I believe, and somewhere else. I'm forgetting the geographic locations, but they're there for long-term deployments to exactly get at this question. Can we resolve temporal variations through these observations, or is it going to be within the noise? So I'm not going to give a great answer here, but what I can at least say is that initial studies of like before and after a volcanic eruption, for example, do indicate that there seem to be large changes or significant enough changes in the responses that we should resolve them with modeling. It's going to be a decadal long problem to solve, because I'm just showing you one inverse model result based on deterministic inversion. I've not talked to you at all about what is the uncertainty of this image I'm showing you here. How confident am I in the absolute resistivity? And that really requires Bayesian methods and other stochastic methods to get at that. So yes, we might be. I'm confident we can detect depending on the magnitude of the change, but it's going to take a lot of work to satisfyingly put confidence bounds, I would say, of how much change occurred. But at the very least, we can say, let's say there was a volcanic eruption. Volcanoes are the easiest example here. Maybe earthquakes are a great one too. But if there's a volcanic eruption and you've depleted that magma reservoir, you've removed a large conductive body. And so it should theoretically be we should be very sensitive to something like that.
Okay, maybe a few final questions here. We have a question that says, I noticed in your inversion results, some of the resistivity value is super low, like below 1 ohm. How much fluid do you think would cause a low resistivity? And they followed up with to say, like, what is the volume fraction and salinity of the fluids that would cause such a low resistivity?
Yeah, so that's a very perceptive question. And it's the reason when I showed this result, I did not talk about porosity at all. Because this is, in my mind, insanely conductive. And remember, this is, let's say the feature is even narrower or smaller spatial scale, and it's being smeared. That means it would have to be even more conductive than is being shown in this figure here. And it's hard to explain that if you're just going to use some typical seawater salinity, let's say, and whatever the temperature is down here, because the porosities would be just unrealistic physically, right? And so ultimately, I think the answer here is it shows how little we know about the composition of these fluids. In shallow part of this, I think we've shown that we can make estimates of porosity that are very bang on, consistent with like what we know from drilling studies and what we expect from modeling studies, geodynamic simulations as well. But some of these deeper features where we basically, what is this fluid here? I know I'm saying it is a fluid, but what is it and what is its composition? Is it highly saline? Is it a brine? And that all that information is necessary to get at how much fluid is there. So it's both a minus and a plus. It's an opportunity, I think, in the future to try to get at the composition of these fluids if we can have some other independent observations of how much might be there, we can start tackling what the composition is. Otherwise, when I see superconductive stuff, I stay away from interpreting it because it's super challenging, other than generalized tectonic interpretations, because it's challenging to put numbers on some of these things.
Okay. All right. Just a couple final questions. So question here is, could MT results identify deep-rooted forearc faults reliably, or would it only be able to resolve faults that have a high hydration level?
That's a great question. I mean, those kind of questions, I would say, really need additional modeling studies. Just like create a synthetic structure that looks like this that you drew, right? And then generate some synthetic forward data from that, add some typical noise and do an inversion and see if you can recover that structure. I would say that, it really has to do with the contrast and the material properties. As we get deeper, things do get smeared out in our inversion, but even if it's narrow, if it is conductive enough, we will just see a broad thing that's harder to interpret on its own. But then if you give me some seismic imaging results that tell me, hey, this thing is relatively narrow, then I can incorporate that information into our inversions through prejudicing them and get a better idea of what the resistivity structure is. So it's not the best answer, but it really shows you how little we've done in terms of synthetic studies beyond some of these first order really obvious examples. If you want to get at those details, we really need to do a lot more. They're not the sexiest or most exciting thing to do, but they're great information to have, especially for motivating places to go do additional surveys. Can we resolve this feature? If we can't, is that a data limitation, or is that really because it's not there?
All right, maybe we'll wrap up with a final question here. Wondering if you could comment on the level of cooperation between the marine EM community and the seafloor geodesy community. Ship time is expensive, but it seems like there are clearly overlapping goals.
That's an interesting question I haven't heard before. I would say by all means we should be having those conversations. I think for sure scientifically, there's no doubt. I think I've already shown here the value of both those types of data in addition to seismic and really any other kind of geophysical, geochemical, geological data set from the offshore world. It has a great amount of opportunity for integration to make cool discoveries. I think if the question is about shared ship time, then it gets into logistics, right? So for us, when we're deep towing our instrument, we can't really be doing anything else besides recording what's happening in the water column through the ship's own instruments, I should say, specifically. Whereas if, let's say, we're just doing an MT survey and I'm throwing some receivers off the side of the ship, there's absolutely opportunity for jointly doing surveys. As a matter of fact, at least on the seismic side, I have a project coming up with a colleague who we're going to be deploying simultaneously OBS, ocean bottom seismometers, and our EM instruments all over the Cocos Plate in about a year from now. And they're going to happen together at the same time. And that won't be the first time that's been done. It's been done before. Geodesy is relatively new to the game, kind of, in a sense. And so it's great to think about. So I welcome that conversation, or at least I can point you to the right people if you're interested in sparking up those discussions.